I want to talk, yeah.
I wanted to mention, I think the difference between the chaos and the order is Bombay population is half of the state of California.
Yes.
So 2 Bombays is the entire state of California.
Yes, I think
so. Would it work if we use the logic of our cities versus that chaos theory?
Yes, answer is yes. You asked for it. Well, basically, what I think we have to learn to deal with masses of data. We have to find a way. So there are many ways. So you have, for example, the other Dutch guy, Winnie Maas, Datascapes, works with massive amounts of data. But the other thing is, what does this piece of data represent? And then I want to go in a higher resolution. And well, but the essence is we have to learn to work with massive amount of data. So it's not interesting to think of 1,000 points, no. Tens of thousands, millions of points are actually all the reference points that are describing your environment. So the relation with Bombay is evident. Yeah? Millions of points, millions of people, millions of this or that. That's why we have to work with. We have to find a way to work with that. And you cannot imagine this with your head. Your brains are too slow. You cannot imagine how things rotate in space. It's impossible. Your brains are not fit for that. So you have to find a way to cooperate with the speed of the computer. I think that is one of the bigger tasks of today. How do we work with that? Not as a stupid device, but work with that in the design process and enhance, expand your design possibilities. Well, I see that as the challenge. Water pavilion, that's where we started, with actually having curves, the power lines, having the reference points, expanding the reference points to subset of reference points, describing everything. We didn't make a drawing to make it. So forget drawings. It's about scripting. And scripting is exactly precise. And of course, scripting relates to the manufacturing, to the CNC production, because the machines, they read the data. They don't read drawings. So drawings are only actually for your building permit that someone can stamp it. That's the only way where that drawing still exists. Well, more data coming in from sensors, informing the light environment in the water pavilion, always changing according to that emotive vector formula, which is, again, completely irrational. Scripting, like a sort of game for urban design, where we can play with all sorts of parameters that are connected to those objects, and objects are connected to other objects, and there are attractors that actually are aligning objects, there are repellers, etc., etc. So everything is related in a parametric system. And in the end, you can have a direct translation into architecture from that parametric system. So now we come to that component level, which I keep emphasizing. This is an example of, and that's another name I have some difficulties to remember. That's her. That's her. Yeah, yeah, that's her. I think these are quite repetitive, these components, but what I like is the airiness and the lightness of it, and there's a relation with the structure, by the way. That structure is not exactly correct in its execution, but I think it's a big step forward. Another way of thinking of components is, of course, this what's the exact name of it? Quadcopter. The quadcopter actually picking up the stones and placing them one by one. Well, you all know this example. So also in the assembly, well, this gives the promise that also in the assembly phase, it's important to have an identity of each component and identity of the relation with the neighbor, the exact position of it. But of course, I would never choose bricks to to work with. I would make my components as unique components and then have the quadcopter placing these components. So what we do here in Hyperbody, in my research group, we have 4 giant robots. And we have this as basic material, and we use something like this, which is a hot wire that can actually move in space and can describe all sort of complex forms, but still linear because it's a wire. And we also have that with a diamond cutter for harder materials. And then we can make things like this. Then we can make this as a building component, which in itself is complex, and which combines to other components to form the structure. Well, back then, to a simpler component, then explain how things are everything and all the connectivity to other components is actually embedded in one component already. Okay, so all the shapes are different of that climbing wall. It has one central point from where all these other points, which are necessary for applying these climbing grips. And if the triangle is different, also the pattern of this is different. It's aligned with it. And then we go to the other side, the back side. So this, everything is 3D milled. Oh, the side of this, you have to realize that the side of this triangle has a twist, because the shape is doubly curved. I mean, everyone who has worked with doubly curved surfaces knows this. If you have a weight normal on the surface here, next point you have it here, there's always a twist between those two weight normal. So how do you do that if you want to have a smooth surface? Then you need to go from here to here with the milling machine. It needs to follow that twist. This doesn't need to do that, but it needs to be adjusted in its base, such a way that it can be connected by bolts to the next one. So all the connectivity is in a parametric way, in structure and skin, connected. No, I don't have that image. So behind this, behind the scenes, you have all these connectors. You connect here. And the interesting thing here is that we don't have structure in the node. We have it here, and then it transfers the forces through the skin to the next connector, etc. So the whole thing is very, skin and structure are working structurally together also. Well, there we have this. And there we have reference to nature. And that I show actually to emphasize that we never work from nature as to copy it. I mean, I think that's the wrong way, the wrong attitude. So what we always do, we develop the system, and we develop the project, and afterward it looks like something that you know. And then it looks like a whale, or it looks like a big snake, or it looks like, yeah.
With the climbing gym wall,
Yeah.
were they able to remove components and replace them
Yes,
with new ones?
exactly. That's the idea. Each individual component can be taken out and replaced by another one.
To create higher levels of difficulty? Or
Yes, that's exactly the idea. That's also true for the cockpit. You can always take out one element of the structure, and all the forces are bypassing that hole that you are making. So it's structurally sound, it's structurally robust. Robustness is actually a very good word for this. And that's also done on purpose, of course. And if you calculate, there's another thing. If you calculate a diagrid structure compared to a rectangular structure with how do you call these crosses? Bracings, I think. If you compare, then this diagrid structure uses less material than a traditional structure because of its effectivity of transmitting the forces to the ground. Well, this has another completely other reason to show you. There's not much non-standard about this. I mean, it's almost completely standard all the materials he used, but some of the claddings are done in a non-standard way. But actually, most shocking, I find this. When you enter a Gary building, it's such a platitude, it's such a banality. I'm sorry, he's American. But that's not what I am saying, but you take this right from the catalog. All these things you take right from the catalog, and somehow you have to chop it or adjust it to make the shape. So I think that's not the proper way, again, I had the Calvinist way of saying it. That's not the proper way of doing it. I think you have to make your own catalog. That's the most logical thing. You make your catalog and your building, the set of components you make your building with. So this is the web of North Holland, and even the door is part of that catalog. So it's not that unique catalog. It's not something you take from somewhere. No, you make it. And then the only thing that this door makes it different from this structure is basically the hinge. It has the hinge, and therefore it's a door. Not very unsimilar to car design, where you have a door. When the door is closed, it forms part of that body. And the only thing where it makes the difference is really these pistons up there and the hinges. So that's where we come closer to making products, housing products, house as a product, where you can actually tweak all the vertexes yourself. This is a project that has not been built yet, where the users can tweak all the curves as to adjust their own shape. And that is done through a website, so we already built that in 2000. So you can tweak all the curves. You can see the feedback here, the curves, roof, other curves, sizes, pump it up. And the interesting thing, it's still our design. So it's still our signature, but it's also open to users. That's also their signature. So we become co-designers. More examples of that. Let's quickly go to this. This is the basis for that polynuclear landscape design I showed you before. That's the plot, and the plot has that potential of bottom-up grow emergence. Well, it's very obvious for you as Americans that the plot has that potential. I think it's brilliant. Grid cities are brilliant. So that landscape has the potential to grow from there to, but maybe there is one step more we could do, and that is in another way play with and that's an attractor game we have written in 1997, play with parameters, as to play with the sizes of what you build in this landscape, and play with the cubic meters of water you want to build. So register everything exactly, play with the number of trees, and then make this public spaces, make these combinations, but all based on an exact calculation of how much you have. So this approach could be combined with gridded cities. So for these areas, playing that design game, you know exactly how big it is, these domains for living. And here it was interested to have the ecological corridors in the housing areas. With this as an end result of an urban design for 1,500 houses. And then back to the individual house inside those housing domains. And everything was layered. So if it was water, then this house was in the water. This is also a very typical Dutch approach. We build more and more houses in the water. And if there's no water, we make water to have houses in the water. So the unification is important. This is the facade of our first housing project. This is the patio houses, where we have the dazzle painting wrapped around it, So it's a very simple project, but this is how it communicates with the world. It has a number, it has a phone, and it's a letterbox. If you close the door, if you open the door, it's completely open to the world. But about to unify the project, so this is the unification of the water pavilion. It's all in one material. It's everywhere the same, except here for the panoramic window. Also, the door, of course, is an emergency exit. It's somewhere there. You see the same approach in the De Young for Herzog-Tumeron, exactly the same approach. It's one material which covers everything. Of course, these developments are always preceded in art. You almost always see that everything that we as architects do is preceded in art. So I'm not tired of that, so we can learn from that and we can cooperate with artists. And the other thing is that technology that we as architects typically use is always preceded by product design. There's always making use of machines way before we as architects use those machines. In other words, architects have the tendency to be lazy and very slow in catching up with new realities. So both from the art, both from the intuitive side and both from the technical side. But we are learning. Now, also, therefore, these images are so nice. This is Dubai, by the way, but it's so nice because it's unified by the fog. And then back to our own work, that's what we try. We try to unify the overall image, to have it radical, to radicalize that image. It's not different from Herzog-Tumeron. It's the same attitude. Okay, the other aspect of when you identify all these individual components, all these reference points and the connectors between them, and you can go lower and lower, higher and higher in resolution, you can also actuate them. If you can do that, if you can identify them, you can also tell this point to move. If the connector between this point and the other point is an actuator and not a static one. So that was the basis for this project. It was the design for the interior of a space station, the space station up there, to have one skin that is fully programmable, and you can program this space to be different things, to be a working environment, for example. Computer is very slow. Working environment, that you have sort of a table, or you have this other environment, playfulness, or this the play environment. So you can have these different modes, basically. Computer is now very slow in responding. Next. You can have these different environments that actually accommodate different functions. So this is another way of telling that it makes sense to identify and to think of the component level and have the emergent modalities from there. It does make sense. And also this environment is completely informed by what you want to do. So it can also be informed by functions, by activities. Project we did with Philips, it's called iLight, intelligent light. These are tiles that are intelligent. They are connected to the neighbor by magnets, so you can take them apart. And you can place this tile, you can place it elsewhere here, and then actually it has a circuit, a board inside, and it has a small intelligence, and then it's looking at its neighbor and basically asks the neighbor, what is your state, your color state in this case? And then it negotiates with the neighbor, and then they negotiate to become similar. adapt to the other state. So you can see things happening here. So it works. This style exists. It was experimental phase, but it's not on the market. From car design, this guy, Chris Bangle, BMW designer in the first decade, the zeros of this century for BMW, also wrote a book which is very interesting. So that's why I show this title. Have you ever seen this? It's interesting. You should read it. It's a fantasy about what cars could be, well, say after 30 years. What is a car after so many years? And basically he fancies that cars are no longer this complete body, but actually is made of different components that sort of are looking for each other. So there are a set of wheels there, and there are some upholsteries there, and there's some other parts there. And if you need more wheels, then these wheels would assemble to form that kind of car. So it's much more adaptive in thinking than the cars we have now. It's either this car or that car. But then you could think of cars that could adapt to different functions and different needs. And one of the prototypes he made was this one. It's the BMW Gina. And I think it doesn't run out of itself here. So just have a look what is happening here. So the feature lines, the other irrationality in car design, I mean feature lines, it's not exactly for streamline, but it's for building the character of a car. These feature lines can move. So you can actually, as a owner of the car, you can tweak these lines yourself. You can actually customize the feature lines of your car. I think it's a great idea. And aesthetically, this prototype has been the basis for the whole BMW 5 and later 3 series. So aesthetically, it also has been the basis for the design. So what we've fancied almost in the same period is, suppose you have this building. It's a big, you can see how big it is. It has this three-dimensional skin connected to its structure that is actually composed of actuators, of big pistons, electronic pistons. And you need those pistons that know exactly where they are, so that you can give feedback to the system. If you compose your structure of these pistons, it can expand and shrink, and you can adjust your building to different functions. So this is another idea that is actually quite valid. It sounds a bit far-fetched in the first, but you will see actually how much this has been actually creeped into the minds of many younger artists and designers. This adaptivity of structures that you can adjust to different circumstances. And maybe it doesn't look like this, maybe it's much more distributed, like components that, like this project we did with Festo, maybe it's much more distributed, that you have certain components of buildings that behave differently and can respond to the people that are using the space, or just passengers are using the space, and then the walls, this is a dynamic wall, could then respond to you as a passenger. So you pass by here in the base, and there are sensors placed in the base. These sensors know there's someone approaching me, and then they respond to that. The way they respond, of course, is completely up to the designer, because programming, writing lines of code is designing, there's no difference. message. Then suppose we do apply that to the whole structure. We also made this test with the hyperbody students. There's something wrong here. I'm not used to click with the mouse of a Mac. There it goes. You only have Macs here, do you? You don't use PCs. Why is that? You pay twice the money, and you have half the performance. Okay, so here we have the brains. Here it's external in this case. Actually, it should be embedded. The brains are actually calculating everything that is happening with this structure. Here we have muscles, and these muscles can contract and expand. They either relax or they pump up, and then they become shorter. And then people inside are actually playing with sensors that are built inside. Here's also one, by the way, that opens the door or closes the door. And playing with sensors inside, the whole structure starts to have this sort of massage. A good question would be, why would you do that? No one wants to ask that question. Well, that is still pushing almost a button. The other movements are more vague, so to say. More, it's not random, but more vague. Well, there's one very good reason I have for this. That is, if this was a static image, and now it's a moving image, it's absolutely more interesting to watch something that is alive. Yeah? You can compare it to, I mean, here you have a dead bird, and there you have a living bird. You quickly get tired of looking at that one. Well, you feel pity for it. But that one, it keeps it has your intention, so it catches your intention. So it's a very strong thing to catch your intention and to actually become involved in that environment. So there will be many reasons, many applications for this, I'm absolutely sure. I have to look a little bit at time. There is 1 hour, 6 minutes and 37 seconds elapsed. And well, I was asking for your endurance, so I suggest 10 minutes more. Is that okay? Yeah, then I have to abbreviate some of the rest of the lecture, so I will skip a few things and then show maybe some projects, some larger projects we have built, to have the feet back on the ground. Is that okay? This really brings your feet not back on the ground, because this was our ground zero project, where we imagined this building, which is multi-story building, and this cube actually contains exactly the same volume as the two towers, and we imagined that building to respond to what happens in the environment. So celebration of the Union flag or something completely different. And you see the building, so you must look at the building there. It changes. It changes completely if there is a complete different thing going on in the city. This is possible. So this was what we did on invitation of Max Protech that was I think in 2002, this exhibition. And actually adaptivity was actually our main issue. So we should not resist and we should not fight, but actually we should adapt and include. Inclusion was actually the main issue. We should include different ways of lifestyle instead of resist to that and fight. And of course there was always one moment that you think back, and this volume could actually become the two phantom legs of the World Trade Center. well, sorry to be a little bit shocking here, but it's the basis of it is to adapt, to adapt to changing circumstances. An acoustic barrier that adapts to the train passing by. And the motto for this project is very clear, so now you see it in the relaxed situation. You don't need an acoustic barrier if there's no noise. That's basically the message. So why should we build all those ugly fences around the highways to block the sound if there's not always sound? Well, for a highway maybe it's almost continuous, but for the train it's absolutely not. So once in a while there's a train, and then this acoustic barrier wraps the train as to block the sound and then relaxes again, and can have a life of its own as an art project. It can relax and have some movements, even if there's no reason. Yeah.
Can I ask about the functionality of the acoustic barrier? My understanding is the requirement for sound buffering is mass.
Yes.
And the image that you have is fluid, and it seems thin and.
You mean this image that I just showed? That has mass as well. You need not much, by the way, as a mass.
I mean, there may be a new material to be that we may not even have yet that will provide acoustic insulation that doesn't need to be stiff and heavy and weighty.
No, it doesn't.
Right.
Doesn't have to be. I mean, the requirements for our acoustic barrier was you need 10 kilos per square meter. Well, that's this much sand, for example, in a flexible bag. That would do it already. So it's not that much. And that, well, I didn't invent the rules, but that's the rules that were given to us. And that would suit our situation in Holland at all. So I have to skip a few things now. Okay. I think I go to realized projects. Yes, one moment. Yeah, okay, let's start with this one. A smaller one, the Web of North Holland structure, the play of light on, well, what was exactly the quote of Corbusier? Masses, play of light on masses. Also from the inside, like hot lava, it's coming from the inside to the outside. This is the design, which is the power line, it's the feature line on the volume. Very much comparable to feature lines from cars. Translated into structure. CNC produced, just to give you a very quick overview of how things are done. It's not that advanced. This is a machine that already existed 15 years before we even discovered that it existed. And then you have to realize that we're 15 years before others discovered that it existed. So there's these big periods of time really have to pass before we get to know things. Then each component is unique, and because it's double curved, many components are twisted. They have these, let me see, where can I show that? Why don't I see that? Strange. Well, okay, well you can see it in this one, for example. But actually most of them are twisted. Oh, not these ones, these are not twisted. To accommodate the curvature. Architecture, no, sorry, architecture. Because now it has a function, it has a door, so there must be something in it, so it must be functional, must be architecture. Well, that's the whole difference between art and architecture. Functional use, second use, the structure alone, new detail, in front of the faculty, in front of the burned faculty. This was a tragic moment in 2008. And now that building is completely gone, and we are in a renovated old building. Maybe some of you know that, and actually it's a perfect place to work. This was not so good. Yes, I go now to the, let me see, I think really these sort of facts is good to see. Just go quickly through it. This is the acoustic barrier in the cockpit, point cloud, scripting, not drawing but generating, not drawing, generating the 3D model, generating the exact panels to cut for the glass, generating the exact holes for where the bolts have to come. This is actually a visualization of the structural program of the steel manufacturer. Making it, it's as simple as that. It's just a normal workshop, but it reads data. Making a prototype, always necessary. Identify all the components. Each component has a unique number. Make prefabricated packages of components, bring them to the building site and bolt them together by heavily underpaid workers, I have to say. That is mostly the case, because they don't need to know anything, they only need to know a number, and then putting them all together, and then the dynamic of the shape is formed, and then it forms the shape. So it's very much formation, it's not deformation. It's not like you have a mass and then you make a deformation. No, it's actually forming it. It's a formation. Like the flock of birds is a formation, it's not a deformation. This is Google view, so you can see it. You can see all these buildings on street view. We didn't want to have the acoustic barrier to end abrupt, so that's why we have this feature line, the fault line, and then becoming actually this line that goes all around, and then it continues on the other side. So it has two equally looking good sides to it, not a front side and a back side. The client, happy with the model, physical model, the concept, the node. So this is one of the 300 different nodes constituting the building. Okay, a quick word on evolution. I go very quick now. Separate components, more and more embedded in the body, more and more integrated in the grille, more and more rounding the corner, more and more becoming part of the whole. All sort of lines continuing from here, in the headlight, and then continuing in something that is completely alien to it, but still communicating. And I think that is an enormous progress in body design, and we can learn a lot from car design in that sense. Because usually it's not done in architecture, and I think this is the big future for it. So some of our attempts is a BMW showroom. Well, the Lincoln Continental, that's where I played with as a kid, but now it's important that the Lincoln Continental, the Ford Lincoln Continental, had this ending actually designed from the side and designed from the top and the front, and this Continental, the Bentley Continental, it goes from the side, it goes to the front, so there's a continuity around the whole body. It's much more a three-dimensional design. So that is actually one of the big progresses we have seen in car design as well as in architectural design. So no more side view, no more floor plans. So if I would teach here, I would actually forbid floor plans, forbid side views, forbid sections, etc., and almost forbid drawings. You see cross-fertilization, that this Jaguar this unique feature of the Jaguar, this one, this light that actually comes from that curvature from the side, it's actually already pre-conceived here in this Lancia, and then even better, in this Suzuki Swift, it was already there. And it was 10 years before the Jaguar. So this I find very interesting. So completely different brands and how they cross-fertilize between each other. So there must be a connection. Well, of course, some of these designers, they hop from one brand to another, but that's not the whole story. There's much more to it. Well, there are many examples of this. Now I'm going to finish with some of I have to show this as well. This is my father's interpretation of Mies van der Rohe, a sort of playfulness. So my father was an architect, so the negative corner. But he was playful, so he had these windows that were more playfully. And then 50 years later, that's our own design, that we have sort of incorporated this playfulness, this different sizes also, but we have actually radicalized the corner. And that's actually something I really wanted to show, because that is. So this is the Mies corner, and the radicalized corner, let me see where I can find it quickly. Oh, it's in the end. Well, it starts here. The radicalized corner. So this is the Liwa Tower in Abu Dhabi we have been building. So all these building components are unique in size and dimensions, but when they fit together, but it's very robust, as you can see. When they fit together, they form the whole. And they are in sync with the structure of the skin. So you see a very high definition of the structure. It's very dense. It's also very strong. It doesn't use more kilo steel, by the way, but it's denser in its structure because it has to sync with the skin, and usually the skin is smaller plates of raw material where you have to cut the aluminum from and the glass, etc. So that's where they come together, and then they work together. But now this corner problem, which is no longer a problem, reference point inside of structure refers to a reference point on the exterior of the skin. That's one system. And then this is the logic. Then the reference line here somewhere in the middle, that reference line travels. Where's the corner? Travels towards the corner. And you can see here clearly when I'm looking, this reference line is no longer aligned with this. And it becomes, because it sort of travels to that corner, step by step. Meaning that it's not a fixed relationship, but a dynamic relationship between those two reference points. And only therefore, we can have this corner, which is exactly the same detail as this line, and the fault lines somewhere in the middle. So that is the sort of radicalizing Mies van der Rohe, or in other words, Mies is too much, which I used to say. So both because I like him very much, I very much respect Mies van der Rohe architecture. I think it's super, but still he uses a lot of additional details, which is not necessary if you have a parametric system that actually can cater for all these variances, can cater for all these instances. And that's the inclusive approach. So this approach includes the other approach. Also, it includes rectangular architecture in a different way than the traditional architecture excludes this. So that's the difference. So this includes the other excludes the one. And it is called Liwa Tower because the colors look very much like the Liwa Desert, which is south of Abu Dhabi. It's part of the big, the empty quarter. I would put this as an image behind my desk instead of that image of Niemeyer. So now we are coming to the closing section of the lecture, next generation building. That is building from component level, imposing all sorts of power lines you want to have on that system. They're working with the robots, the components, working with the intelligence. This is the protospace, by the way, this protospace floor, where all these elements are, these are lights, and these are lighted up by the small brains that are built in here. And these brains, they actually work like that, and that is in ICT technology quite revolutionary. They work as members of a swarm. So this brain communicates with this one. So if it radiates some data, this one is informed and then brings the data to this one, to this one. So it sort of has a viral effect from there. Also, this system can be informed top-down, to start from here and then spread. So it's a combination of working together, and now it's a combination of bottom-up and top-down working together. But it only works if this identified component is intelligent. And then we can actuate such a structure. Then it can actually act by itself, and it can also be acted upon. Mouse problem. Well, then, this was my last, well, actually, no, I have to show the set as well, don't I? Yeah, okay, give me 2 more minutes. I come back. Otherwise, I skip too much. But it's not easy to, yeah. Because it's another example of how power lines can inform a system, and it's also a project that relates to existing old buildings as well. So that's where it started. This building in Budapest, and you see the relation with an old building there. And it goes like this. We have 2 warehouses, and we have a lost piece of a warehouse there. And we have a pitched roof, which is like this pitched roof, and then it transforms and it rises up, and then from the top, the pinnacle of the pitched roof, it leaves and touches the ground and forms a body, forms a volume, like this. So here, behind it, this roof, it goes up, and then exactly at the top it leaves, and then exactly there it touches the ground again. So these are the power lines we enforced on the system as to form a big event space inside there, and escalators leading up to that event space. This is then the entrance from the city side. Here you have, by the way, the Faculty of Architecture, which is very interesting because you have some of these old-fashioned traditional teachers here, still in white coats. Remember that? Old days, white coats, and they this paper, big tables, and they're looking at this. Very interesting. It's already used as a venue for marriages. Like here they go to the Japanese garden to have their pictures that we saw yesterday. But it's interesting that they choose these kind of situations to make the wedding picture. So that is the traditional part where we have the three roofs, and then it extends into that body part. And here you can see how dramatically the structure actually comes from there and then almost falls down, and here is a dramatic twist in it. But also it forms a very functional canopy to have a dry side entrance. So there's always one more reason to do something. And maybe that's, yeah, if I would have some real message, then I think it's, and that's for me, that's the definition of sustainability. Always have more than one reason to do something. So if I build an acoustic barrier, I build a building into it. So then I have two reasons. One is acoustics, the other is I have a building. So if there's more reason than one to do something, it's the most sustainable act you can do. And then, okay, the last image, that was this book cover. That will be a new scientific journal. So this is actually really a new side of the profession of architecture, that we are coming much closer to real science. With the kind of work we are doing, and kind of work many architects today are doing, we come much closer to real science, and it becomes interesting to set up a magazine, scientific magazine for architecture. And I call that Text Generation Building. Will be out end of this year, and I will send invitations around actually to send in papers for that one. Okay, I would like to finish the lecture here. Thank you for your endurance.